Let's talk about deep space radiation. Here's all the different types of particles. We've got solar wind, full of auroral electrons and trapped protons and trapped electrons and in the inner zones. And in particular, we're worried about the solar storm protons, the solar flare protons, and the galactic rays. We're existing in this all the time. The sun is constantly off-gassing hydrogen and atoms and wind. This is just the general solar wind. And when it hits the Earth, and a storm does hit the Earth, the magnetic field compresses in the solar direction. And it tries to repel back that onslaught of charged particles. It has for 4.5 billion years. That's why we're here.
In 2014, we drove around the country to meet many of you, discuss and share information about the thing that concerns us most. 41 states, 4 provinces, and tens of thousands of miles later, we had met thousands of you, seen some amazing things, and some amazing places.
So we've lost about 15 to 20% of the magnetosphere right now. If we get down to 50%, we can't do this.
You have to put it all together, like pieces of a puzzle. None of them are hidden, even though some are indeed turned upside down, not immediately projecting their proper place in the bigger picture. The galactic arms are not merely peppered with stars, but with gases and dust and cloudy regions that present an entirely non-homogeneous microscale structure to the arms of the galaxy. We see this is likely to be true of many galaxies, and indeed resembles the larger scale cosmic web as well. There is a massive void in local space known as the local bubble, the remnant shell of numerous supernovae, with the core remaining as the local interstellar cloud, through which we are indeed currently moving. Now, while the supernova void is tremendously sparse, its neutral helium content is the primary source of the X-ray background of the sky, and the local cloud here at the core around our sun is 6 times more dense in hydrogen and is confirmed to be strongly magnetized. It also has a wide array of other elements as well. We are in a supernova remnant after all, and we should consider the oxygen to neon ratios relatively similar to other sources to be a pretty good indicator of the general elemental abundances. It is expressly believed by some at NASA that there is even more oxygen there locked up in the rocks and dust of the cloud, like iron oxide or aluminum oxide, as is much of the oxygen inside of our Earth, which is the mantle's most abundant element, by the way, just in rock form, not the gas we are used to breathing. It is interesting to note that it was the same interstellar or galactic wind that originally misguided some to believe we were heading towards the center of the galaxy that eventually showed our position. It was based on that galactic wind that they published this alongside the cloud image, the chart showing how the older results hinted at our being in the void amidst the empty areas of the interstellar cloud, but how newer data, based on that galactic wind, caused us to now know that we are indeed inside of the local cloud. But that is about to change. You see, while the sun has been on a steady trajectory, the cloud is moving in another direction, to the left. So the sun is more likely to have entered the cloud at where the red arrow is pointing, that portion of the cloud there, but did so many years ago when that portion of the cloud was back over to the right, such that the red and yellow arrows would have been on top of one another. This combined relative motion analysis means we are moving pretty much directly into an empty area within some of the remaining nova core clouds, out of the denser magnetized shroud cocooning our solar system, and literally into the void. Compounding this increase in exposure is the fact that our sun's magnetic protective bubble is dropping in strength, and that is expected to continue as well. This allows more entry of those waves and particles on top of that allowed by our exodus from the cloud in the first place. Now, the sun has been very strong recently, stronger than it has been in about 11,000 years. This has provided a large amount of protection for the last century or so, but all evidence suggests that it is about to drop out hard in the coming decades, with a lackluster return over the coming centuries that is almost certain to miss the mark set by the recent multi-millennium maximum. And the cosmic ray forecast based on that drop in solar activity alone presents uncharted territory in modern science. So to review, we are right now coming out of the grand solar maximum since the end of the glacial period. We are about to see a tremendous drop into grand solar minimum, followed by a very slow magnetic recovery that won't likely reach those same maximum levels for thousands of years, allowing for that uncharted territory of high cosmic ray flux.
And so I come back to these pillars, and I take a look at this idea of an equatorial ion fountain and how this, especially on the sun side, is compressed a little bit extra by the solar wind. If we have a space weather event, it can be compressed even more. And all of these papers that are coming out, sunspot maximum versus sunspot minimum. All right, we'll just go with sunspot minimum. More negative phase ENSO, more negative phase PDO, negative phase NAO, NAM, SAM, a disruption of the ENSO's control over the Pacific North American connection and a more variable intertropical convergence zone. What do all of these things mean when our electromagnetic interface from space is changing? The same goes for cloud nucleation, lightning, and hail formation, except these might be a little bit more easy to understand, because as we come to these huge, massive processes, like when we had the fifth paper that discussed solar cycle effects on ENSO, they're still mostly focusing on these statistical correlations, which are very convincing, but the mechanisms do feel like guesses, and they're not really purported to be much else than that. They're purported to be their best hypothesis. But what we do know is that on these smaller scales, in terms of whether it's direct aerosol production or air ionization, cosmic rays play a role in clouds. They play a role in lightning, and they play a role in hail formation. So this article was probably one of the best articles so far that has come out climate-wise in 2018. This was the folks out of Princeton describing how every single existing climate model was underestimating the cooling effect of clouds.
The fact that this happens it happens throughout history, and we're here, so we survived it. We don't need to be playing God in the sky, only if we're really trying to control the situation.
Now, as if uncharted territory in cosmic rays wasn't enough, and with us already leaving the larger magnetic cloud of protection, there is still one more magnetic shield to discuss, our own.
A review quickly of a lot of what we already know, a lot of what has come out of NASA, a lot of what has come out of ESA Swarm, what has come out of Berkeley, and some of the implications and what we can derived from that based on an interdisciplinary look at some of the other studies that have been done. But let's begin with where we've been and kind of where we're going here. So this is the North Magnetic Pole. The color change and the distance between the dots is indicative of a few hundred years ago. The pole was doing what it is supposed to do, move a few miles every few years or up to a decade, and sort of meander around the polar region. All of a sudden, about 150 years ago, it started going faster and faster, and it is now racing across the Arctic Ocean. About 5 years ago, it blew past the geographic North Pole, and this is basically what we're seeing. It's heading towards Siberia. Let's review what's going on with Antarctica. It is not moving anywhere near as quickly, but it decided it didn't want to go back over the geographic pole, and it has already left the continent of Antarctica. We all remember this, yes? Then, of course, we have this very scary curve that I wish didn't exist. Because essentially, we are coming off of geomagnetic maximum power about 3,000 years ago. And it was sort of a rapid geomagnetic spike. It didn't last very long, but even the period just before it and just after it can be considered the geomagnetic maximum of this planet, at least recently. And it started to decrease in strength very, very slowly. The WDC, the Center for Geomagnetism in Kyoto, Japan, estimates that it was losing, maybe a quarter of a percent, every couple of decades, or even up to a century. But then, when compared to the magnetic field strength in the 1800s, NASA, in one of the most read articles from this period of the internet, you can find it. It's an article that I have seared into my brain called Earth's Inconstant Magnetic Field. They reported that as of the year 2000, Earth had lost about 10% of that magnetic field since about the 1800s, which was much faster than had been expected, much faster of a field strength change over time. Clearly, if you can do the math, if you can lose 10% of your field over about 150 years, that's not a normal thing in the tens of thousands, hundreds of thousands of year time scales where we're talking about a magnetic excursion or a magnetic reversal. But then, of course, it was just 10 years later in 2010 when we got the word from Rune Flåbergagen. Now that is a great name, isn't it? Does anybody know who Rune Flåbergagen is? Mission manager, ESA Swarm. Basically on par with NASA's MMS mission. Slight differences. But in 2010, they needed to upgrade that figure. They said that we had gone from losing about 5% of the field per century to 5% per decade. And they put that 10% figure from back in 2000 at 15% down at 2010. In 2015, they neglected to give us a new percentage down, but Rune said that the trend was continuing. Earth's magnetic pole movement and Earth's field weakening are related to one another, and Earth's magnetic poles are getting ready to flip. That is the mission manager of ESA Swarm. You can Google that exact statement and find where it was absolutely blasted all over the internet after he said it. And so we have this situation where we have the changing magnetism of the planet, but it's not changing homogeneously everywhere. What we know now is that we have this rapid intensification of the movement of at least the North Magnetic Pole occurring simultaneously with this rapid loss of the field, the kind of thing that is not what you see over the thousands of years. I mean, you just do the math. You lose 10% over 150 years, then you lose 5% more in just the next decade. That is how you get that curve. That is simple math. It is not difficult. Of course, there is always the possibility that the Earth could buck this trend that's been going on for millions of years and just stop doing what it's doing and everything's going back to normal as I'm sitting here speaking to you. I like to bet on what we can observe and the trends that we do see. All right, so we had a couple of years ago, USGS and Occidental say that a magnetic reversal can happen once it begins to really get going in as little as 150 years. And then Berkeley came out just 2 years later and said, oh no, that's actually as little as 80 years. So it was very interesting to see that we generally think of these magnetic reversals as taking thousands and thousands of years to happen. Well, there certainly are many more years than that between them. But once it starts to happen, there is evidence. Again, the first study was from USGS and Occidental, and then Berkeley came and confirmed it. that these things, once they get started, can happen in less than a human lifetime. And quite obviously, we are more than 80 years into this one already. And we are seeing the intensification, the speeding up of the pole movement, and the speeding up of the loss of the field.
It doesn't seem to make any sense. The only ideas I've come up with, they just sound crazy in my head, and I don't share them very often.
But it's like holding two magnets, you know, if you hold it in a certain field, there's a repulsion.
A consistency of reports from around the world of catastrophes that are amazingly similar. But a lot of people thought it's just what people dream up when they have a lot of time or they're dreaming or whatever. It's just stuff that people naturally come up with.
What you're seeing now is just some of the last 2 years of peer-reviewed papers on pre-seismic anomalies of the electromagnetic nature. Hundreds of them preceded these before 2016, and now the maturity of their correlations have led to a NASA project involving electromagnetic pre-seismic anomalies, and China and Italy's launch of a satellite to detect these signals before earthquakes. Total electron content, thermal infrared emission, magnetic field anomalies, all able to forewarn of seismic activity because part of the seismic process is electromagnetic. Now let's back up and get the big picture. We reframed those studies under the over-electrified Earth scenario due to cosmic energy. Back to those earthquakes and volcanoes. By the way, this is not the same flurry of papers you saw at the start of the video. There are literally that many, and there are dozens more that I couldn't hope to find them all, let alone have time to show them in this video. The totality of them is not the point. The point is the recognition, and beyond that, the involvement of the sun. Sure, it is much more recognized by Chinese, Russian, Indian, actually pretty much every other region than it is in the United States, but even that acceptance is growing. After all, our paper with NASA's Dr. Wu Yan and Ohio State's Dr. Holloman got published, and it was all about the sun and earthquakes. The only thing stopping energy from space from having a greater hand in Earth's electrical processes is the magnetic field. The geomagnetic and geoelectric systems already link the ground to outer space, and cosmic rays are already known to penetrate to ground level. Simply put, everything about the electrical processes of earthquakes is going to get a boost as Earth becomes more exposed to the galaxy and beyond. However, it may indeed be the volcanoes presenting the ultimate concern. With John Casey and others predicting significant upticks in volcanic eruptions during solar grand minima, we are forced to look at the very convincing studies on silica-rich magma viscosity intensification due to cosmic ray bombardment, especially because a completely independent group of researchers just made the same discovery on 2 levels. Let's quickly also remember the potential of volcanic eruptions to play in the climate and cool the Earth. Now back to the new news. The cosmic ray signature on volcanoes is visible in both the duration and intensification of volcanic dust indices, the ones indicative of how much volcanoes are cooling the Earth. Not only does the wavelength match suggest forcing modulation on the 11-year solar cycle, but the lagged inverse amplitude correlation suggests it is based on cosmic ray surges.
The last time we had this solar shutdown, the magnetosphere was really strong. Our magnetic poles were stable. It wasn't until the last Maunder minimum ended that the poles began shifting and the magnetosphere began weakening.
As the lithospheric emergence points for Earth's field, the magnetic poles tell us a lot about what is happening. They are supposed to wander a bit, but the south has wandered straight out of Antarctica, and the north is on a tear across the Arctic Ocean, dwarfing hundreds of years of movement in just the last few decades. This, concurrent with the weakening of Earth's magnetic field, sets a future of magnetic reversal for our planet. Earth, Sun, and local cloud all provide a magnetic bubble, and each is in the process of becoming less of a protective factor for our Earth. Those energetic sources from the galaxy and beyond will get an easier run through all 3 primary magnetic shields into the atmosphere, and we already know cosmic rays reach the ground and penetrate already. Earth's weaker magnetic field is going to let in more of everything that comes by: sun, galaxy, and those far away. A weaker sun means less magnetic protection from the rest of the galaxy and, again, those far away. And as we come out of this local cloud, a large magnetic cocoon, that leaves us with the fall of 3 major protective magnetic shields for our planet. Now, who likes whipped cream? Okay, so not to ruin this rosy masterpiece of universal attrition, but there is one other aspect of this that would be worth consideration at very least. Remember what the cloud is: magnetic hydrogen. There's also a lot of oxygen in there, both in gas form and likely trapped in the rock, where well understood charge exchange mechanisms have demonstrated the extraction of that oxygen from the rock in asteroids of our own solar system to combine with hydrogen into water. It can certainly happen here too, and there is likely those polar water molecules aiding the magnetic character of the cloud. Now, what happens in your home, say during a humid versus dry day, or hot versus cold? You are most likely to get a static shock on a door handle when it's cold and the humidity is low. This is because there is less of a distribution and spreading out of that energy in the dry, sparse air. From the solar system scale down to Earth's magnetic field, it is difficult to tell exactly what some of the exact effects would be from entering an area of higher static potential. That would be the bubble. But somebody should probably be thinking about it. In this episode on Earth's magnetic flip, we'll pull back from seeking out official information and connecting the dots, and we're going to focus instead on some key questions that come up over and over again. First one is about timelines. When is this going to happen? Well, that's a very tough question. It's happening now. Do you mean when we have the flip? When will things get bad? When will things go back to normal after things get bad? Many ways to read that question, but the simplest way I can think of to answer it is with some modeling. It can be done even with limited data. As we come to look at a chart of Earth's magnetic field strength, presuming a baseline of the 1800s, which had persisted more or less a long time before that, we know that in the year 2000 we had lost 10% of Earth's magnetic field, shown here as 90 for 90% compared to the 1800s, and then the 15% loss number updated in 2010, shown as an 85 here, for 85%. What comes next are the best case, worst case, and middle of the road, based on that limited information that a slowly changing magnetic field kicked into a weakening phase that saw 10% of the field lost since the 1800s, and then another 5% in just the next 10 years. The blue line shows what happens with no further speeding up of the process. The yellow line shows a continued acceleration over shorter and shorter periods. Red line is merely the middle of the road between them. While this graph is indeed helpful for figuring out how little of our magnetic field will be in play over time, it indeed does not tell us when things will get bad. That's likely a personal definition for each of you anyway, and there's no real way to tell if that's 20%, 50%, 70%. We do know that the field tends to retain at least 5 to 10% of its strength during reversals. What we can say is the fact that these lines confirm Berkeley and the previous work by the USGS and Occidental indicating that these events can happen rapidly within a human lifetime. I doubt that question about when things will get bad is one that anyone could answer, nor exactly to what extent cosmic rays will intensify at the Earth system. However, we could put our heads around something similar and include the fact that our sun's motion relative to the local dust cloud has us exiting it over the next couple of decades to centuries and going into an empty pocket. This indeed is the third shield against cosmic rays that Earth is losing right now. This chart will require some explaining. The blue area shows the total universal radiation. And indeed, being inside the Milky Way only provides a minute bit of protection, given that for every bit of the sky shielded by other stars, there is an object much closer that could produce energetic radiation. The blue area begins to recede strongly within the local cloud. The dust may be relatively sparse as we would consider it, but it is vast and it blocks out radiation the further in you go. The solar magnetic fields of the heliosphere around our solar system take out much, much more, and so do Earth's magnetic fields. But as we come out of the local cloud, we are watching one shield against this radiation disappear. The pink area is the luxury we have enjoyed inside the cloud. As we exit, it'll be disappearing in favor of the blue. And then as the sun enters grand solar minimum, we are already seeing the highest cosmic rays of the space age, and we do expect it to go much higher. The dark yellow is the reduced radiation that, again, we have enjoyed as a luxury during solar grand maximum the last few decades. And lastly, we've got Earth's magnetic field weakening as well. Now at this point, we do see the lines begin to converge as nothing really stops the highest energy of all particles. But alas, the green, yellow, and pink have been our luxury, and we are indeed headed for much higher rates in the future. Thus far, our weather look in the magnetic reversal has been a long-term one, a climate-forcing expectation based on the currently published literature, and taking it a bit further with the grand solar minimum coming, the recognition of cosmic rays and solar activity as having a modulating effect on lightning and other short-term weather phenomena goes back well before those seismic, volcanic, and long-term weather connections to space. Over the last few decades, much driven by Dr. Brian Tinsley out of Texas, an incredible amount of information on space energy and lightning, cloud formation, atmospheric ionization, hail, nucleation, and more has been steadily coming out. Cosmic ray-induced particle showers are so well understood to have effects on short-term cloud properties that even the IPCC recognized the need to investigate these cosmic connections to terrestrial weather. Today, the effects on ice nucleation, cloud condensation, and lightning showers are well recognized, even if we're still trying to figure out the minutiae of how it all works. So now, just like before, as Earth's magnetic field weakens and the sun enters grand minimum this century, should we be looking beyond the recent Princeton bombshell about the cooling effects of clouds? The best summarization of the air shower cosmic ray effects is electric. The cosmic ray particle cascade starts off as one super energetic proton breaking down into muons, electrons, neutrons, and photons as it collides and scatters its energy through the atmosphere. More lightning storms, more lightning strikes, stronger lightning strikes, more cloud cover, and higher variability of that cloud cover, easier freezing of supercooled water into more larger hail, and there is even considerable evidence growing in regard to wind speed correlation with solar wind parameters. All the things that make these correlations true have to first overcome the magnetic shield of our planet, and in terms of cosmic rays, the sun's magnetic shield as well. That means that the weather can only intensify as the electric cascade from space intensifies.
When you don't have plasma and electricity, you don't have any way of explaining these crazy stories. But once that becomes available, now they're all explainable. And it's a whole different way of looking at things. This is all new in terms of the plasma and the electricity.
Let's come to section 6.1 of Weatherman's Guide to the Sun. I started that chapter with the most certain of studies and the most repeated and confirmed. Terminal arrhythmia, especially in those with ventricular dysfunction. It's a big risk during space weather events. Now this could be why. Normally we get electrical activity across the heart muscle, but in ventricular fibrillation, a vortex of electrical signals, an electric tornado in the heart, can stop it in an instant. Now at this time, the mechanistic connection is hypothesized here, but we know this type of issue has a major connection statistically to terminal outcomes during space weather, and we must only then ask if the electromagnetic forces of space weather are capable of affecting an electric tornado. Something tells me it can.
Now that we know how the secondary radiation evolution happens during a galactic array impact, isn't that a good theory for the evolution of genetic mutations over time on Earth? If this has been hitting us since we began, then we're getting mutations in cellular tissues and maybe even genetic tissues every day. And that's really a source of evolution, not just natural selection, that's part of it. But it's the effects you have to worry about. You get neurobehavioral decrements in anxiety, fatigue, and performance, cataract formation, damage to the quiescent neural stem cells in the hippocampus, increased skin cancers, degenerative circulatory system damage, prodromal effects such as nausea and vomiting, skin burns, changes to bone and muscle and so forth because protons kill bone marrow. If you get hit by a big enough solar storm of protons and it kills all your bone marrow, you don't make any red blood cells. If you don't make any red blood cells, you're dead in 2 weeks because your body's constantly replacing them. And here's why it's dangerous. X-rays can damage the nucleotides. Heavy ions and galactic rays can bust it apart. And we've already seen this in astronaut post-flight chromosome damage, where we've got busted chromosomes, violation insertions, and a lot of the astronauts, 39 of the former astronauts, suffer from cataracts from space travel.
I've been into Canada since I was about 4 years old. My dad took me to Niagara Falls. I don't remember going through customs or doing anything like that. A little nervous.
Do you want to drive for a little while?
Disturbs me the most, right? It's like, if we had 1859 again, what are they going to do?
The Carrington event in 1859 is where it actually broke the field. Minus 1900 nanotesla event that busted through the magnetic field and ignited all of the telegraph lines on Earth.
I'll admit to feeling a little bit of ridiculousness. I had to come to Canada and have crappy internet to realize just how dependent not just the channel was, but how dependent I am on electricity. It is a realization of a personal vulnerability and realization of a, I guess, more general vulnerability.
How close we came to a major solar disaster. And what I'm talking about is what happened at the end of June earlier this year. We came closer than I think anybody really realizes to having major issues. And since I initially started making this presentation, I've had to update it every single month. In fact, I was updating this presentation just this past week because I had to. The sun and its interaction with Earth was producing effects that I promise you are not supposed to be seen with this level of effects. Let's take a look at this right now. So if you guys remember, if you were watching, in late June we had a little uptick on the sun. A number of solar flares and coronal mass ejections were released. They were released from this sunspot. It has a beta, gamma, delta magnetic classification. And the important part of that is where the blue and the red are colliding over on that one side, where you can sort of see that circle with the negative. That's actually my cursor. As you guys know, if you've seen the Sun series or if you watch regularly, where we get that blue positive and that red negative colliding in close quarters in the sunspot, that's where you're likely to get the flare energy, or at least the destabilization event that sets off a solar flare within the sunspot. You may also remember, thank you, Trevor, you might also remember that these coronal mass ejections, a number of them were fired directly at Earth. What you're looking at here is a coronagraph image, and the reason why we have a circle in the center appearing to sort of block things is because if we didn't have that circle in the center there, the sun's glare would completely wash out the image. This is a very sensitive camera. It's meant to pick up all those little lines and all those particles of ejecta, those charged particles in the coronal mass ejection. And so what you're seeing here, when it looks like this, we call it a halo eruption. This means that it's coming right at Earth, because when there's an eruption on the sun and you have a satellite that's looking directly from Earth, it's going to expand as it comes towards you and look a little bit like a halo. Well, that's exactly what happened in late June. And after a number of coronal mass ejection impacts, we saw what equaled the largest geomagnetic storm of this entire solar cycle. You're seeing that as the red spikes on the right side. This is known as a level 4 geomagnetic storm, G4. And we have only had a few of those in this solar cycle. What you see over to the left, you see the blue and the red curves, and what that is that's known as the magnetometer. And to simplify, that's checking to see what sort of disruption there is in Earth's protective magnetic shield, the magnetosphere, due to space weather. And as you can see, there's a pretty good ding right there. Most of the time, even when we get a strong impact from the sun, we do not see these curves dip into the negative. And in fact, what this means, and I've only seen this 2 other times with solar events, is that for a brief period, about 2.5 hours, this coronal mass ejection impact actually whipped around and reversed the magnetic field for a little bit. And technically, when the magnetic field readings are at 0, technically, there is a large part of Earth that was Earth's shield that was magnetically neutral and letting solar plasma pour right into the atmosphere. And so this is a fairly significant event. Now, what did we have going on during this event? At the peak of the storm, nearly simultaneously, these happened minutes apart, the entire aviation radar system of New Zealand went down, which is one of the things you look for when you have a solar event. And the FNB digital banking system, which is the largest national banking system in South Africa, also went down. These happened within minutes of each other at the peak of the geomagnetic storm. Now, the interesting thing, when you have the geomagnetic storm, that can induce these electric currents and cause these disruptions all over the place. But when the magnetic storm ends, that is not the end of the story, not by a long shot. You see, that energy starts coming down layer by layer if it doesn't immediately get funneled down into the Earth through the magnetic fields. And so after we see these geomagnetic events, the place you look next for disruption is the atmosphere. So, just a few days after this event, the solar impulse plane, I don't know if you guys know about this, it's the first completely solar-powered airplane. It was making a flight from Japan to Hawaii, and it fried its batteries as it went through the atmosphere. They made special considerations for this in the manufacture of the plane and in the housing of the batteries specifically to guard against this. Now, why do I say that there's a chance this was related to the solar event? Because this is exactly where the atmospheric disruption occurred after the geomagnetic storm. We had 6 tropical cyclones pop up in the Pacific Ocean, and there was one of them that was a strong candidate. We almost had 7, and that has never happened before. There have never been 7 simultaneous cyclones in the Pacific Ocean, at least not during the time that we've been watching. But indeed, there were 6 within just a few days after that, and as you can probably tell, this is the wind map, and the cyclones are the tight circles where it spins in. And I've got the precipitable water overlay on here so that you see some white and some light blue crowding the tropical storm. So you can really pick out where those tropical storms are. Now, the solar impulse plane, when it's fried its batteries, it was going from Japan to Hawaii in the exact area where 4 or 5 of these storms can be found. Is that definitive proof that the solar impulse plane frying its batteries was triggered by the sun? Absolutely not. But there are some coincidences you shouldn't write off as being, oh, that's just a coincidence. Things like this, we may never actually find out one way or another with 100% certainty. But things like this stay on the radar. So we had the ground events in New Zealand and in South Africa during the storm. And as that energy was as expected, coming down through the atmosphere, we saw the solar impulse plane fry its batteries, and further indication that a lot of that energy that hit Earth and caused that storm was heading into the Earth through the atmosphere right in this general area. And as you can see, this 6 tropical cyclones hadn't happened since 1974. Before that, you got to go back a really long way. And this was the earliest formation ever of 3 typhoons in the western Pacific. Keep this slide in mind because we're going to see it again tomorrow afternoon. Further evidence that this solar event was major. It turns out that at the time that the sun fired these events at Earth, hiding right behind Earth from the sun's point of view was Ceres, the dwarf planet, and directly behind that was Pluto. A few days after Earth's storm, Dawn had to go into safe mode at Ceres due to an electrical event. And a few days after that, New Horizons had to go into safe mode at Pluto. But the point is that all the ways we have to determine whether or not this was a major solar event are kind of giving us a big thumbs up. We saw one of the strongest geomagnetic storms of the solar cycle, the strongest the strongest disruption on the magnetogram of this entire cycle. Ground events, atmospheric events, and it just so happens that everything on a line from the, with Earth and the sun had some sort of glitch that day. Now, is it possible that Dawn at Ceres and New Horizons at Pluto just coincidentally happened to both go into safe mode in these days following that, and they think they were electrical events? Of course it's possible that it's a coincidence. It's also possible that it's not a coincidence, and the timing of these things tells us a little more. So, I've sort of explained generally what happened, but I have not at all answered the question, how close did we come to actually seeing a major solar event? Well, that question is hard to answer, at least in terms of, what, are we 5 away? Are we 10 what away? What units? It's a very difficult question to answer, but when you compare the solar events that just did this to us this summer with some of the other solar events that we're used to seeing, it doesn't paint a very friendly picture. So, what we have here is some basic space weather information. We have M-class solar flares, which is where, at least for me, solar flares begin to get significant. Not all M flares are significant, and some large C-class flares are significant, but at M range is where we start to get significant. And then we have X-class solar flares, which are, X-class solar flares are about 10 times powerful than the M-class solar flare. Then we have major flares and mega flares. Just kind of keep this in mind and how much more powerful you get when you move up a level. It's not like you go 1, 2, 3, 4. You don't go 1, 2, 4, 8. It's by powers of 10. So, looking back to just the last solar maximum, there were multiple X10 flares, hundreds of X-class solar flares. And there was only, let me go back for a second, there was only that one ground event of all of those in Sweden. Do you guys hear about the Sweden blackout of 2003, the Halloween storms? Out of all the X10 solar flares, out of the hundreds of X-class solar flares, there was only one ground event. Let's come to the first part of this solar maximum, 2011 and 2012. The largest solar flare we have seen this solar cycle was only X6.9. We have not seen any major ground effects from anything in 2011 or 2012, and there was one satellite issue in 2012. If any of you remember the early March solar flares that actually released gamma rays, it was one of the first times we've ever detected gamma rays instead of just X-rays from a solar flare. This event actually took out the SkyTerra station. It was completely devastated by this event in 2012. But still, just very, very few events. In 2013 and 2014, The biggest solar flare we saw was only X4.9, and we saw no ground effects, no satellite effects, nothing. So here we are in 2015, and we've seen something fairly significant. And what we're looking at here, these are all of the solar flares responsible for that huge magnetic storm at the end of June, the one that took out the radar in New Zealand, the one that may have fried the solar impulse plane's batteries. Don't know if you guys can read that, but we have no mega flares. We have no major flares. We have no X-class solar flares. In fact, we don't even have any large M-class solar flares. These are all low to mid M-class range. And yet, look what they were able to do to Earth. There's a bit of a disconnect there. This is the solar wind of the major impact that caused the storm. And what you're looking at on the top line, which is supposed to look a bit orange, that is the density of the solar wind. It's relatively dense. The next row is the plasma speed, how fast these particles are hitting. And that's above average speed, but certainly not anything you're going to cry home about. In fact, we had a coronal hole stream just this last week that pushed the solar wind speed near 900 kilometers per second. Here, we don't even hit 800. Down below, there's about a 10x increase in the plasma temperature on the Kelvin scale. With big solar impacts, we can see a 100x increase in plasma temperature or more. And so, somebody like me who has studied every solar event going back as far as they have really been able to track these things, I look at what the sun did with the only moderate flaring. I look at what came in the solar wind, and it's above average at best. And then I look at what happened to Earth, and I say to myself, how in the world did this just happen? What if that was an X-class solar flare? What if those were X10s? Things that just a few years ago we were taking without issue. The idea that Earth is responding to these solar events differently is something we're going to talk a lot more about tomorrow. But let's come back to what's been happening this year. A little bit after I started this presentation, and keep in mind that that KP8 event was in late June and some of the effects bled into July. But in August, we had another KP7 event. This was off even smaller M-class solar flares, even weaker than the ones that we saw in June. At the peak of this storm is when that Washington, D.C. blackout occurred that took out the radar. You guys remember when those hundreds and hundreds of flights were grounded from Virginia and West Virginia and Maryland? That occurred at the height of the storm. And there's absolutely no way that should have happened. In September, we had two separate KP7 events, which is a level 3 magnetic storm. And the first one, at the peak of the storm, that transformer caught fire and blew up in Ireland. The second time it happened in September was when we got the San Diego blackout. And you guys might remember, we talked a little bit more about this on our Fly on the Wall podcast because this was a very significant event. The San Diego blackout was not an electrically induced fire or explosion. They actually shut the power off because on their side they could see energy was rising to levels that should never occur, and they had to shut it down or they were going to lose every transformer in their system. Now, interesting thing about this is the peak power plant from SDPG&E, which means that it is built specifically to handle those peak power times. You know, in Southern California, when it's 2 or 3 o'clock in the afternoon and it's the middle of the summer and it's 110 degrees and everybody is blasting their air conditioning. That's what this power plant was built for. In the evening, in September, when it's not really that warm, so much energy got surging through there at the height of this storm that they had to shut it off. Again, are these definitively solar-induced events? Of course not. We will probably never know. But when there's this many coincidences and the timing is this good, we're not talking about, oh, these things happened one day and the next day. We're talking hours and sometimes minutes between the peak of the disruption and some of these events. You can't really just write it off. And so, does anybody remember the beginning of October? I think it was October 1, October 2 in the news. There was this major plasma filament. I mean, look at it compared to the size of Earth. And this was, you guys remember a news earlier this month where I said Earth got lucky? Yeah. This is that coronagraph image you saw earlier with no eruptions whatsoever. And you can sort of see some lines, but this is what it looks like when the inner heliosphere is quiet, when the sun is not producing eruptions. And then the eruptions began, one after another, including 3 that combined into one as that filament released. In total, 8 coronal mass ejections released in one direction over the span of 48 hours. The 3 biggest ones over the span of 1 hour and combined into each other. This completely missed Earth, and we are very, very lucky it did. I couldn't quantify for you how close we came back in June, or in September, both times, or in what I'm about to show you from just a couple days ago. But I can tell you that if Earth was 3 months ahead in its orbital period, this coronal mass ejection would have hit us. And this is a lot bigger than that one from July 2012 that NASA said was a kill shot, was as big as the Carrington event that would take out global power and set us back a decade just to even get going again. If you go and you take a look at what that eruption looks like, this one is bigger, this one is faster, and this one has multiple CMEs in succession, which is the thing that can really be almost more important than the magnitude of the solar flare. You get a bunch of these eruptions hit Earth one after another in short succession, it can be as though a much bigger event happened. Well, this is 8 in a row, and 3 combined into one of them that was way bigger than what we saw come in July 2012 that NASA says would have done some major damage if it had hit Earth. And also, I don't know if you guys can see in the top right there, there's almost like a tube, a white tube that you can see amidst the clouds. That is the leading edge of one of the coronal mass ejections, and I have spent hours and hours scouring through the images. That is unmatched in the coronagraph images. I've never seen anything like that, and I couldn't even begin to tell you what would happen if that hit Earth. It's not like you'd be standing there and it would fry you on the ground. We're still talking about electrical problems, but boy, the electrical problems could have been really major. And so these are just some of the other coronal mass ejections. This one occurred just 4 hours later, and it itself was relatively large as well. So we had those 8 major coronal mass ejections. I would say 4 of them were probably major CMEs. I think that one was a kill shot potential. And what I mean by that is it takes out the global power grid. It's the kind of thing where the transformers across the world do start blowing one by one by one, where the ground currents are such that, you could see fires in homes, things like that. I mean, heck, just think about what happened back in 1859. The telegraph wires caught fire. The telegraph operators got shocked. They unplugged the telegraph machines, and yet the telegraphs kept transmitting back and forth. We're talking about major, major influences here. Luckily, this one missed Earth. Let's come to October, because just days after that, we saw another level 3 magnetic storm. And yes, this is the one that was just a few days ago. Now, was this X-class solar flares? Was this M-class solar flares? No. This was a coronal hole stream that triggered this. So we're not even talking about a burst, an eruption from the sun, just a speedier part of the solar wind. These types of things should not be happening with this moderate or an even puny level of space weather. But nevertheless, near the peak of the storm, we had a melted power line in Washington State, just a few miles away from the Priest Rapids Dam explosion, which they also said was electrically related. Very tough to ignore those two things so close together when they're like that, especially at the peak of a storm. We also had the transformer fire in India, and I am still looking into the loss of power across the entire country of Belize that occurred during that time. I can't tell you definitively that that one's a great candidate, but it's certainly a candidate. And the transformer fire in India and the two electrical disasters in Washington are very, very good candidates for having been affected by this geomagnetic disruption. And so this leaves one asking, what exactly is it going to take? You know, if you had asked me this question, what's it going to take for there to be a global blackout? For there to be that solar kill shot? If you had asked me that in 2004, well, first, I wasn't looking at this stuff in 2004, so I would have looked at you like you were crazy. But had I been looking at this stuff and paying close attention, I would say, look, we take X-class solar flares, we take X10s and higher. And I'm thinking it would probably take an X25 to X30 before we really start having to worry about non-localized effects, stuff on a global scale. If you had asked me in 2011 or 2012 or even 2013, heck, if you had asked me in April of this year what it takes for the sun to send us back to the Stone Age, I would have said, no doubt, X10 or higher. Unquestionably. If it's less than that, you don't need to run for the hills. You don't need to be scared. But look at what's happening. We saw a major magnetic storm and effects from M-class solar flares. We saw, just a month later, even weaker solar flares do it again. Those two events we saw in September, there were no solar flares, there were no coronal holes. These were small plasma filaments that ejected away from the sun. And yes, this last one in October was a coronal hole stream. If you ask me today what it takes for there to be a global blackout, I really can't tell you with any sort of confidence, especially when we can see what happens with very, you hate to call it minor space weather because of what it's done on Earth this summer and this early fall, but it's minor space weather. This is not major space weather events whatsoever, and yet we are seeing a vulnerability of our systems to these events. What I do know is that we are seeing an increased vulnerability of Earth to these things. I hope you have a general idea of how close we have come this summer to not being here right now. To me, not being able to post that news every morning. For you not being able to use your cell phone or use the email or do anything. Came a lot closer than I think anyone really realizes. Anyway, thank you.
Now, let's take some time to go over some basic prepping notes. No way to do this comprehensively in this video or in one video alone, but we can get you started. I want to hit 2 points right now. How should you prepare? And are there some areas in the world that are going to be in worse trouble than others? Let's start with the basic prepping. So as to not overload all at once, let's get our heads around some of the basic things you need in any emergency, long or short. It's good to have food, water, and supplies, including for yourself, your family, and your pets. The other basic part of this is keeping your head out of the sand. I assure you that you won't be hearing major updates from CNN, reality TV, celebrity Twitter accounts, etc., so making sure you are paying attention to the right places is probably one of the best ways you can prepare. However, the Earth's magnetic reversal, combining with solar grand minimum, presents some challenges to the basic prepper. These events may not be short-term. In fact, they are unlikely to be, especially when we are talking about the potential grid effects. At the National Space Weather Forum in Washington, D.C. last year, I sat listening to how unprepared we were, how our electrified way of survival can be taken away in a matter of hours. And since only a handful of groups have all the contracts for emergency aid pretty much everywhere, it is commonly believed that such a business model is based on things not getting too bad in too many places all at once, certainly not everywhere at the same time. So, what else should you consider? The first thing that comes to mind for this non-comprehensive list, please do recognize there is so much more, is the long-term need for that food and water, not to mention those medicines and pet supplies that might apply to your personal situation. Our government says we could be down months to years, so seeds and tools and books on how to live are useful in that type of life. Maps on local areas, goods to barter, especially vice goods, clothes for extreme weather, etc., but also the mental side of things. Local ways to survive, the plants, trees, the insects, mushrooms, the terrain, the waterways. And what about your neighbors? Do you have a bug-out plan? What about a bug-in plan? If you can stay in your castle, it is always best. You're starting to get the picture of how comprehensive a mental exercise this can be, in addition to the physical preparation. But let's now go to an overview of areas of the world that are likely to be under duress. I absolutely did move my family across the country. Now, this is not a move everyone can or should make. My job is here online and can be done anywhere. My wife is our CEO and is capable of anything, and my kids are not yet in school. Not much tying me back. I am not willing to bet against all the available data I can find or the patterns of our planet that have persisted since long before humans started their first fire. If I could even find one clue that we were not on the verge of a reversal, I'd say so. But I can't, and I chose a place I find suitable against many future hardships. Let's take these one at a time. First thing that comes to mind is the coastline. Not only are there a lot of people, and people means chaos in an emergency, but the earthquakes and tsunamis, including those from subsurface ocean volcanoes triggering landslides, means that the coastal regions present a major concern, even if you're not at a major fault line. Do you know how to spot the pre-tsunami warning signals? Could be the difference between survival and something else. Even on the U.S. East Coast, where they don't have major earthquake risk, they have the Canary Islands across the Atlantic and the Puerto Rico Trench waiting for a landslide to send a massive wave at the coast. We mentioned the high population areas already, and this one is pretty simple. More chances for chaos, less resources in a disaster, crowded exodus from weather or tsunamis. One of the most basic location safety points is you wouldn't want to be in Times Square when everything bad begins to go down. Let's step down to the severe weather events. It's not like you'll see tornadoes in Death Valley or Mount Everest or even here in the high desert, but areas that see them could see more. The breadbasket is going to see hailstorms like they've never seen before. The wind, precipitation, ice, flash flooding, all intensifying. So picking your battleground is important. For us here in New Mexico, there are no quakes or tsunamis, not really any tornadoes, and less of the other severe risks as well, provided you are not living in an arroyo. We also have a low geomagnetic vulnerability profile. Mid-latitude is by far the safest in terms of space weather. Polar regions take the strongest induction, and that does indeed bleed down into the United States. The practical reality for us humans is that the risk is a combination of population density, or rather electric grid density, grid usage, along with your geomagnetic latitude, which is why you see increased potential even during calm days down the coastlines. However, one can't simply head south from Canada per se without looking back. Get too far south and you come under duress of the equatorial electrojet and the magnetospheric compression of solar eruptions reinforcing the downward precipitation of Earth's equatorial ion fountain. and adding Van Allen particles to the precipitation as well. We do indeed see equatorial excitation and risk potential growing along the equator with the polar regions. And let's not forget the South Atlantic anomaly is there, the most prolific upsetter of satellite GPS in the space age. Now, thinking back to high latitude risk one more time, the last note is one about cold. Since cold records doubled heat records last month in the US, since snow records continue falling, since Princeton described a cooler future than models predict from above, and Yale did so from below, and with our current interglacial overdue for a major drop in temperatures on this planet, one must caution against the warming-only propaganda in the news. Climate change absolutely goes both ways, and with the sun going to sleep as our shields falter, it's a recipe for deadly cold events if you are too far north or south. Now, there's no place for fear in this. Fear is a thief of your time and focus, but make no mistake, in almost every way imaginable, these changes on Earth and Sun are extremely concerning and merit your attention. Eyes open, no fear. Be safe, everyone.